Assalamualaikum and hi, my name is Izzah and meet our team members.
Hi!
For our calculus project, we will teach you on how to do this particular question that involve the use of derivative and graphing techniques. As you can see here, there are 6 steps that will be used to solve this question. For the first step, we want to test either the graph is symmetry to y-axis or x-axis or to the origin. The concept of symmetrical test is when we substitute negative x, negative y or even both to the function that we are working on and the answer gives the same like the original function, then we can say that it is symmetrical. So for the first one, we want to test either the graph is symmetry to y-axis. So we have to replace every x in this equation into negative x, and at the end we get the same answer as the original function, which means that the graph is symmetrical to the y-axis. So the graph might look like this. So we do the same to the x-axis, but this time we replace every y in this equation into negative y. So at the end, we do not get the same answer as the original function, which means that the graph is not symmetrical to the x-axis and it will not look like this. The last symmetry test that we will do is symmetry to the origin. This time we replace every y into negative y and every x into negative x. So at the end, we will not get the same original function, which means that the graph is not symmetrical to the origin. That is all from me. I will pass this presentation to Hanis and she will explain how to find the intercepts.
Hi, my name is Hanis. In step 2, I want to show you how to find the intercept-y and the intercept-x from the graph. First of all, to find the y-intercept, x must be equal to 0. So we're gonna rewrite the equation here. Instead of using x is equal to 0 and solve it and get 0.25. So basically y-intercept is going to be in order pair, which is have the x component and the y component. And it makes x point in coordinate system here. So y-intercept represented by x component is 0 and the y component is 0.25. So this is our intercept from the graph quadratic equation. Next, to find the x-intercept, y must be equal to 0. So from the equation f(x) equal to 0 represented by y is equal to 0. Then we can get the two value of x, which is first 0.58 and the second one is negative 0.58. So basically we know that in our quadratic graph, you can get 2 points of the coordinate system, which is first is negative 0.58 for the x and the y is 0. And the second one is for the x 0.58 and for the y is 0. Here is what we can get in our quadratic graph. This is for the y-intercept and this is for the x-intercept. So I will pass this presentation to Shahmi.
Hi, my name is Muhammad Shahmi, and for this part we will look at step 3, which is find vertical asymptotes. Vertical asymptotes are line or lines correspond to the zero value of denominator. It simply means you have to equate the denominator of function with 0 to find the vertical asymptotes, like this. We will get negative 2 and 2. These two values, which is 2 and negative 2, are the values that lie perpendicularly on x-axis where the vertical asymptotes are. The value of function might be going infinitely large or small as x approaches these two values. You can see the vertical asymptotes are perpendicularly lie along the x-axis. Now I will pass down to my friend Munjahau.
My name is Manjahau, and then I want to explain about step 4, which is determine the behavior of function x or fx and derivative test application. Okay, so determine the behavior of function x is the set of a point where x-intercept or vertical asymptote occur is -2, -0.58, 0, 0.58, and +2. Okay, they are the points that divide the x-axis into open intervals. So this is the first interval, which is -∞ and -2. And the next is -2 to -0.58. And then is -0.58 to +0.58. And the next is 0.58 until 2, which is +2. Okay, the last is the +2 until +infinity. Okay, this 1, 2, 3, 4, 5. This 5 interval, which is a domain or a graph range. Okay, so the first step is determine the graph behavior around vertical asymptote using limits. So this is our question, which is question 1. Okay, is a function x is equal to 3x power of 2 minus 1 divided by x squared minus 4. Okay, now I want to talk about determine graph behavior around vertical asymptote. So in this equation, we found that our vertical asymptote is x is equal to +2 and -2. So now the first thing we need to use is a limit. We just limit x is equals to +2 from right hand side. Okay, from the right hand side, which is 2.01, 2.001, and 2.0001. Okay, after we substitute all the value into this x, we will find out that the value is almost near to +infinity. Okay, so next is we use also limit x is equal to +2, but this time we use from the value from left hand side, which is 1.99, 1.999, and 1.9999, and so on. Okay, and then we will find out that the value is almost near to the -infinity. Okay, so from the graph we can see that this is from the right hand side +2, and this is from right hand side -2. Okay, the left hand side +2 will go to +infinity, and then the positive left hand side of 2 it will go down negatively, so it is -infinity. Okay, and it is same with the -2 also. We will find out limit x equals to -2. This is from right hand side, it will go on to -infinity, just like that. And then the limit x is equals to -2 from the left hand side, it will get a positive value. Okay, same as the +2. So this graph is the behavior of function x. Okay, now we want to determine f prime x, which is first derivative. Okay, in this step, we use a formula which is quotient rule. Okay, so let u is equals to fx and v is gx. Then this is the formula. Okay, we just use the formula and then we will get a negative 22x over x squared minus 4. Okay, after f prime x is determined, or the first derivative is done, okay, so we need to find out what is the critical point of this equation. So we find out the critical point with f prime x is equal to 0, which is this, and the denominator of f prime x is equal to 0 if the f prime x is undefined at critical point. Okay, so first thing is when f prime x is equal to 0, okay, we can find out that the critical point is 0. And then when denominator of f prime x is equal to 0, okay, we just use this the denominator of this function, which is x squared minus 4 power of 2 is equal to 0, we can find out that the critical point, there are two critical points, which is positive 2 and negative 2. Okay, after we find out the critical point, okay, what we need to do is the first derivative test. So the first derivative test is use the critical point in a form of an interval, okay, to find out the relative extreme, which is relative maximum or minimum point, okay, and the behavior of fx with first derivative test. So in the interval we use is negative infinity smaller than x, and x is smaller than negative 2. The second interval is negative 2 smaller than x, and 0 is bigger than x. And then the third interval is 0 smaller than x, and x is smaller than 2, positive 2. Okay, the last interval is the positive 2 is smaller than x, and the x is smaller than positive infinity. So we use test point is negative 3, negative 1, and positive 1 and positive 3. So this is the value we find out that from the interval. Okay, it is a positive value if the interval is negative infinity smaller than x and smaller than negative 2. Okay, so it is positive. So the behavior of fx is increased, and then and so on. Okay, so the this interval is positive, so it also increase. Interval is negative, can decrease, and the last interval is negative also, it will decrease. After we calculate all the interval, we can draw a graph like this. After draw the graph, we can determine the relative extreme. So when x is equal to 0, the relative in extreme is relative maximum point. This is because the graph, this part of graph is curved upwards. And then after this, we need to determine the f prime prime x, which is second derivative. So find the f prime prime x for second derivative test to determine the concavity of a graph, and the quotient rules also involved in this step. So we use the equation from the first derivative test, and then we just use the quotient rule again, and then we just find out that second derivative test of fx is equal to 66 x squared plus 88 divided by x squared minus 4 power of 3. That's all for me. Thank you.
Hi, it's me again, and now we will look further on this new equation that we have got. This equation is important for us to know the concavity of the graph, because as in the first derivative test, we have already determined the linear shape of the graph. So we need to know the concavity of the graph then. Now we need to identify the concavity, which is it is concave up or concave down. In order to do that, we have to do the sign of f double prime test. And in order to do the sign of f double prime test, we have to look up for the boundaries. And how we can get that? We have to follow this step. Step 1, we have to equate the denominator of f double prime x with 0. That will lead us to get x equal to 2 and negative 2. Step 2, we have to find the values of x as f prime is equal to 0. Notice that we have to find for the prime and not double prime. And fortunately, the value of x as f prime is equal to 0 is already calculated. That is x equal to 0, and now we have collected up these three desired boundaries, which is negative 2, 2 and 0. Next, we have to build up the table to see the pattern of the sign. Like this, we put in the interval and we test each of the interval, and we get this set of sign. that if we sketch the concavity from the sign, we will get this preview sketch like this. And for the inflection point, we have to equate f double prime x equal to 0, which you can see here. The whole calculation will bring us to get the imaginary solution. Whenever we encounter these imaginary numbers or no real solution in your calculator, keep in mind that for the f, x or function, there is no inflection point exists, and that is what oftenly occur on the rational function. And I think that's all from me. Thank you.
In step 5, we want to determine the end behavior of the graph with horizontal asymptotes. In other words, we want to know where is the horizontal asymptotes. As I've mentioned before, we want to determine the end behavior by computing the limits of fx as x tends to positive infinity and limits as x tends to negative infinity. So if either limits has a finite value, then it is the horizontal asymptote. So as you can see here, we try to calculate what is the limit of fx as x approaching positive infinity, and at the end we get 3. So in the graph, it will look like this. So as you can see here, x approaching to positive infinity, but they will never touch 3 at y-axis. And the horizontal asymptotes in here is at 3.
To determine end behavior, we have to calculate limits of fx as x represents to negative infinity as well. So when we solve the equation by using this formula, we can get 3, which is when limits of x tend to approach negative infinity. It also can get 3, which is horizontal. As x approaching to negative infinity, they will never touch 3 because 3 is our horizontal asymptote. So this is our end behavior graph, which is that will not touch 3 even x close to the left or x close to the right. In step 6, I will show you the sketching graph with all of the information provided. So, at the graph of fx will look like this, where 3 is the horizontal asymptote. For negative 2 and 2 is our vertical asymptote.
We have reached to the end of this video, and we hope that this knowledge will be beneficial to all of us in order to sketch graph, especially when we are dealing with rational function. That is all from us. Thank you for watching.
Bye.